Hey everyone, welcome back to Prep with Sid. So far on this channel, we have spent a lot of time solving SQL problems. But I want to start adding another important area of data engineering interview preparation, which is system design and data modeling. And there's a reason for that. With AI, writing code and even solving many SQL problems has become much easier. But understanding how to design a system is a different skill. You still need to understand the business problem, decide how the data should be modeled, choose the correct grain, identify facts and dimensions, and explain the trade-off behind your design. These skills become especially important as you move into senior staff or principal level data engineering roles. So today, we are not going to write SQL from the beginning. Instead, we are going to take a real e-commerce business problem and design a data warehouse from scratch using Kimball dimensional modeling principles. We'll build the model visually, and at the end, I will show a few SQL queries to demonstrate how the warehouse can answer business questions. Here's the problem. Imagine we are working for an e-commerce company. Customers place orders, and each order can contain one or more products. The business wants to analyze revenue, number of orders, units sold, customer behavior, product performance, sales over time, and sales across different locations. Our job is to design the analytical data warehouse that supports these questions. Kimball gives us a very simple but powerful process for designing a dimensional model. First, you select the business process. Second, declare the grain. Third, identify the dimensions. And fourth, identify the facts. Let's walk through those steps for our e-commerce problem. The first question is, what business process are we modeling? In this case, we are modeling sales. A customer buys one or more products as part of an order, so sales is the business process we want to measure. A real e-commerce warehouse would eventually have other business processes as well: inventory, shipment, returns, payments, marketing, and so on. But we don't try to put everything into one model. For this design, we are focusing on sales. Sales is our business process that we are modeling. Step 2 is to declare the grain. This is probably the most important decision in the entire design. We need to define the grain. Grain simply means what exactly does one row in our fact table represent. We could make one row represent an entire order, but imagine an order contains a laptop, a mouse, and a keyboard. If we only store one row for the order, product level analysis becomes difficult. Instead, our source system already gives us something much more useful: the order line item. So our grain will be one row per order line item. If an order contains 3 products, that order will create 3 rows in our sales fact. This gives us the lowest useful level of detail for sales analysis. Once we commit to this grain, every dimension and every measure in the fact table must make sense at this exact level. Now let's move on to step 3. Once the grain is clear, ask a very simple set of questions about the business event. Who bought the product? What did they buy? When did they buy? Where was the order associated with? These descriptive contexts become our dimensions. Let's start working on the dimensions. The first dimension is customer. This answers the who. We generate a warehouse key called customer key. We also retain the source customer ID. Then we store descriptive customer attributes such as name, city, state, segment, country. This allows the business to analyze sales by customer or customer characteristics. Next dimension is product. Product answers the what. Again, we have a warehouse generated product key and retain the original product ID. Attributes like product name, brand, category, and subcategory give us different ways to analyze sales. Then we have date dimension. This answers the when. A date dimension gives us consistent attributes for days, weeks, months, quarters, years, and potentially fiscal calendars or holidays. Instead of every analyst repeatedly deriving these values, we define them once and use them consistently. Then we have location dimension. For sales analysis, I might want the actual shipping location from the order rather than simply the customer's current home address. That's an important distinction. A customer may move later, but the historical order was still shipped to the original location. So for our example, we'll model the shipping location separately. You will notice that the dimensions contain both a warehouse key and the source ID. You see a customer key, a product key, date key, location key. These are called the surrogate keys. The source ID identifies the record in the operational system. The warehouse-generated key gives us control over how we manage dimension records and history inside the warehouse. This becomes especially important when dimension attributes change over time. We'll cover that in detail when we discuss slowly changing dimension in another video. Now you get to step 4, which is to identify the fact. In Kimball dimensional modeling, facts are the measurements produced by the business process. An easier way to remember it is, facts are the things the business wants to measure. For our sales process, we want to measure quantity sold, unit price, discount amount, sale amount, and cost amount. Now we can build the sales fact table called fact_sales. Remember our grain, one row per order line item. So I include order_line_item_ID to preserve traceability to that source transaction. I also retain the order ID because multiple line items can belong to the same order. Then we store the dimension keys, the date key, the customer key, product key, and location key. And finally, we store the measurable facts called quantity, unit price, discount, sales amount, and cost amount. Now let's put everything together. The fact table sits in the center. The dimensions surround it. This is the classic star schema. Here's the simplest way I think about it. The fact table tells us what happened and what we want to measure. The dimension gives us the descriptive context around that event. And that descriptive context is who, what, when, where. Who means who was the customer, who made the purchase. What means what product did they buy. When, the date, when was the order placed. Where is where the order was shipped, or it could be a customer location where the customer stays, or where the customer lives. These are called the descriptive context around that event. Now let's zoom into the keys and try to understand the star schema relationships. The fact table contains the dimension keys. Customer key connects to dim customer, product key connects to dim product, date key connects to dim date, and location key connects to dim location. That allows us to take the measurements stored in the fact table and analyze them using attributes from any of these dimensions. Okay, so now we have looked at the star schema. We know how the data warehouse will look like, and that shows the analytical side of our model, of our system, right? But we want to understand how the whole system is going to work. What is the source system looks like? And when I say the source system, it is basically the operational model. A business may be using different systems. For example, customers may be managed in Salesforce. Orders may be managed in SAP. Order line item probably lives with the orders or within SAP. And product, maybe there's some catalog software the company may be using where they maintain all their products. So you have these different systems that manage the source data. So the application organizes data around operational entities and transactions. The warehouse reorganizes that data around a business process and its analytical context. So what we do in a system, we basically have operational model or operational systems, and we transform that into analytical model so the business can run their analytical queries. Now let's place our dimensional model inside the larger warehouse architecture. The operational systems generate our source data. We ingest that data into a raw or staging layer. Then we transform it. We clean and standardize the data, apply business rules, generate warehouse keys, build dimensions, and load the fact tables. Our dimensional model then becomes the analytical layer used by the dashboards, the analysts, finance teams, product teams, and potentially AI or machine learning applications. So we have spent all this time designing the model. Now let's see why the star schema makes analytics simple. Okay, imagine we have our data warehouse ready. Now the business is ready to use it to ask the questions. Now the business wants to know, what is revenue by product category? The measure is revenue, comes from the fact table. The way we want to slice that measure is by product category, which comes from the dimension. If you look at the query, I'm taking the fact sales to measure the revenue, and then I'm joining with the product table on a product key to get the product information. Because of the dimensional model that we have created, that query becomes really simple. Let's take another question. Now business wants to know, what is the revenue by month. Here you can see we're using the same fact table, but instead of slicing and dicing by dim product, we are slicing it by the dim date. So we are slicing revenue by the time, and which comes from dim date. Okay, let's look at the third business question. What is the revenue by customer segment and category? Here you can see dimensions can be combined. We are analyzing revenue by customer segment and product category. We could just as easily analyze sales by month and category, state and customer segment, brand and year, or many other combinations. Let's go back to star schema for a minute. You must have heard people talking about slicing and dicing. This is what people mean when they talk about slicing and dicing the data. The fact provides the measure. Dimensions provide the different ways we can analyze that measure. One important architecture point I want to make: if the business later asks us to model inventory, shipment, or returns, I would not simply keep adding more columns to fact tables. These are different business processes with different grains. They should generally have their own fact tables. So there would be a fact inventory, fact shipment, fact returns. Those fact tables can still share common dimensions such as product and date. This is how a dimensional warehouse can grow across the enterprise while maintaining consistent definitions. Here's some interview advice. If you're asked to do something like this in a system design interview, don't immediately start drawing tables. Start by asking questions. What business process are we modeling? What questions does the business need to answer? What is the lowest useful grain? What dimension describes the event? What measurements belong at that grain? Then build the model. And most importantly, state your assumptions. There's rarely only one possible diagram. Interviewers are usually interested in how you reason about the design. Let's recap the process. We started with the business requirement. We selected sales as our business process. We declared the grain as one row per order line item. Then we defined the dimensions called customer, product, date, and location. Next, we identified the measurable facts. Then we combined everything into a star schema, and finally we saw how the dimensional design makes analytical queries straightforward. The biggest takeaway from this video is that data modeling starts with the business problem, not with tables. SQL tells us how to query the data, but dimensional modeling determines whether we have structured the data correctly in the first place. And as you move into more senior data engineering roles, being able to explain these design decisions become increasingly important. In a future video, we can take our customer or product dimension and solve another very common data modeling problem, slowly changing dimension, type 1 versus type 2. Thanks for watching Prep with Sid, and I'll see you in the next one.